Nearly 1 billion miles from Earth, a moon larger than Mercury shrouds itself in an atmosphere so thick that standing on its surface would feel like swimming in cosmic honey. Titan, Saturn's largest moon, possesses atmospheric pressure 50% greater than Earth's, the only moon in our entire solar system with a substantial atmosphere. This isn't just a scientific curiosity. It's a cosmic anomaly that challenges everything we understand about how moons form, evolve, and retain the gaseous envelopes that make complex chemistry and potentially life possible. Our solar system contains over 200 known moons, from tiny irregular chunks of rock to massive worlds rivaling planets in size. Europa hides vast oceans beneath its icy crust. Io spews volcanic sulfur across its tortured landscape. Enceladus shoots geysers of water vapor into space. Yet among all these diverse worlds, only Titan wraps itself in a dense, multi-layered atmosphere that creates weather patterns, seasonal cycles, and surface conditions unlike anywhere else in the solar system. The mystery deepens when we consider Titan's cosmic neighborhood. Saturn itself formed far from the Sun, where temperatures were cold enough for nitrogen and methane to condense. Yet somehow Titan captured and retained an atmosphere composed primarily of nitrogen, the same gas that comprises 78% of Earth's atmosphere. Meanwhile, massive moons like Ganymede, Callisto, and Europa, despite being larger or comparable in size to Titan, remain essentially airless worlds with only the thinnest wisps of atmospheric gases. This atmospheric paradox becomes even more puzzling when we examine the physics of atmospheric retention. Small worlds typically lose their atmospheres to space through various escape mechanisms: thermal escape, where molecules move too fast for gravity to hold them; solar wind stripping that blasts away atmospheric particles; and impact erosion, where asteroid collisions blow away gaseous envelopes. Yet Titan not only retained its atmosphere, but developed a complex atmospheric chemistry that creates methane clouds, nitrogen rain, and hydrocarbon lakes that dot its surface like an alien version of Earth's water cycle. NASA's Cassini mission, which studied the Saturn system from 2004 to 2017, revealed Titan as one of the most Earth-like worlds in the solar system, despite being composed of entirely different materials. The mission's Huygens probe descended through Titan's thick atmosphere in 2005, becoming the first spacecraft to land on a moon in the outer solar system. The data transmitted during its parachute descent revolutionized our understanding of atmospheric dynamics, revealing wind patterns, temperature gradients, and chemical processes that operate nowhere else in our cosmic neighborhood. The atmospheric composition itself tells a story of cosmic evolution that spans billions of years. Titan's atmosphere consists of 95% nitrogen and 5% methane, with trace amounts of hydrogen, argon, and complex organic compounds that form through atmospheric chemistry. This methane isn't just a passive component. It drives active weather systems that create methane clouds, precipitation events, and seasonal atmospheric changes that reshape the moon's surface over time scales from days to millennia. Understanding why Titan alone developed such a substantial atmosphere requires exploring fundamental principles of planetary science, atmospheric physics, and the cosmic processes that shape moon formation throughout the solar system. The answer involves Titan's unique size, distance from Saturn, formation history, and the chemical inventory available during the early solar system's evolution, when the giant planets and their moons were still taking shape. The implications of Titan's atmospheric uniqueness extend far beyond academic curiosity to questions about habitability, astrobiology, and the conditions necessary for complex chemistry to flourish on worlds throughout the universe. Titan's thick atmosphere enables surface pressures that allow liquid methane and ethane to exist stably, creating the only known lakes and rivers of hydrocarbons in the solar system. This exotic chemistry might provide insights into alternative biochemistries that could operate on worlds vastly different from Earth, Recent discoveries have revealed that Titan's atmosphere creates conditions for organic chemistry so complex that it produces molecules found nowhere else in the solar system. Atmospheric interactions between methane, nitrogen, and solar radiation create a photochemical smog containing hundreds of organic compounds, from simple hydrocarbons to complex nitrogen-bearing molecules that might serve as building blocks for alternative forms of life. The atmospheric dynamics on Titan operate according to physical principles similar to those governing Earth's weather, but with materials and temperatures that create entirely different phenomena. Methane vapor evaporates from surface lakes, rises through the atmosphere, condenses into clouds, and falls as methane rain that carves riverbeds and fills lake basins. This methane cycle parallels Earth's water cycle, but occurs at temperatures of -290 degrees Fahrenheit, where water ice becomes as hard as rock. Seasonal variations in Titan's atmosphere result from Saturn's 29.5-year orbital period around the Sun, creating atmospheric changes that play out over decades rather than months. These long-term atmospheric cycles affect cloud formation patterns, precipitation distribution, and the global circulation that transports methane and other compounds around the Moon. Cassini's 13-year mission captured only a fraction of one Titan year, leaving many questions about long-term atmospheric evolution still unanswered. The magnetic field interactions between Titan's atmosphere and Saturn's magnetosphere create additional complexity through processes that strip away atmospheric particles while simultaneously providing energy for atmospheric chemistry. Unlike planets with strong magnetic fields that protect their atmospheres, Titan exists within Saturn's magnetic environment, experiencing particle bombardment and electromagnetic effects that both threaten and energize its atmospheric systems. If you're fascinated by cosmic atmospheres that challenge our understanding of planetary science, subscribe and hit thumbs up. And here is a question that will guide our exploration. If you could give any moon in our solar system a thick atmosphere like Titan, which would you choose and why? Comment below. I'll pin the most creative answer about how that atmosphere might change that world. Tonight, we're diving deep into atmospheric physics, moon formation, and the remarkable cosmic circumstances that made Titan the solar system's only thick atmosphere moon. We'll explore how this distant world captured and retained its gaseous envelope, why other moons failed to achieve similar atmospheric success, and what Titan's unique atmosphere reveals about the conditions necessary for complex chemistry to flourish throughout the universe. The journey ahead will transform how you think about planetary atmospheres, moon formation, and the delicate cosmic processes that determine whether worlds develop the gaseous envelopes that enable weather, seasons, and the complex chemistry that might support life. Now, let's begin our exploration of the solar system's most atmospheric moon, where cosmic chemistry creates wonders that exist nowhere else in our celestial neighborhood. Chapter 1. Atmospheric giant Titan stands as a colossus among moons, its massive bulk wrapped in an atmospheric envelope so dense and complex that it fundamentally alters how we understand what moons can become when cosmic conditions align perfectly. With a diameter of 3,200 miles, Titan surpasses Mercury in size while maintaining an atmosphere that would make Earth seem modest by comparison. A gaseous shroud that extends hundreds of miles above the surface and creates atmospheric pressure 1.5 times greater than what you experience at sea level on Earth. The sheer scale of Titan's atmospheric mass challenges our intuitions about moon atmospheres. While Earth's atmosphere has a mass of approximately 5.15 times 1,018 kilograms, Titan's atmosphere weighs roughly 1.19 times 1,019 kilograms, more than twice as massive, despite covering a surface area less than one-third that of Earth. This atmospheric density creates surface conditions where the atmosphere itself becomes a significant factor in geological processes, weather formation, and the chemical evolution that has operated for billions of years. Understanding Titan's atmospheric magnitude requires examining the fundamental physics of atmospheric scale height, the vertical distance over which atmospheric pressure decreases by a factor of E, approximately 2.718. On Earth, atmospheric scale height averages about 8.5 kilometers, meaning that atmospheric pressure drops to about 37% of sea level value at that altitude. Titan's scale height reaches approximately 40 kilometers, creating an atmosphere that extends much higher above the surface and maintains significant density at altitudes where Earth's atmosphere becomes negligibly thin. The atmospheric composition reveals the chemical complexity that makes Titan unique among solar system moons. Nitrogen comprises 95% of Titan's atmosphere, providing an inert background gas that allows more reactive components to survive atmospheric chemistry without immediate oxidation or chemical destruction. Methane accounts for roughly 5% of atmospheric composition. That this seemingly small percentage drives weather systems, organic chemistry, and surface geology through processes that have no parallel elsewhere in the solar system. Trace atmospheric components include hydrogen, 0.1%, argon, less than 0.1%, and dozens of organic compounds produced through atmospheric photochemistry. These trace gases, while present in minute quantities, play crucial roles in atmospheric chemistry and create the complex organic haze that gives Titan its distinctive orange appearance when viewed from space. The organic chemistry occurring in Titan's atmosphere produces molecules ranging from simple hydrocarbons like acetylene and ethane to complex nitrogen-bearing compounds that might provide building blocks for alternative biochemistry. The atmospheric pressure distribution across Titan's surface varies with altitude and topography in ways that create diverse environmental conditions within a single world. At the deepest surface locations, atmospheric pressure can reach 1.6 times Earth's sea level pressure, while elevated regions experience somewhat lower pressures that still exceed Earth's surface conditions. These pressure variations affect the stability of liquid methane and ethane, determining where surface lakes can exist and how atmospheric surface interactions shape geological processes. Atmospheric layering on Titan creates vertical structure that rivals Earth's atmospheric complexity while operating at temperatures and pressures that enable entirely different physical and chemical processes. The troposphere extends from the surface to about 40 kilometers altitude, containing most of the atmospheric mass and all of the weather activity that creates Titan's methane cycle. Above this lies the stratosphere, where photochemical reactions driven by solar radiation create the organic compounds that eventually settle to the surface as hydrocarbon sediments. The discovery of Titan's atmosphere required sophisticated, remote sensing techniques that could penetrate the dense organic haze surrounding the moon. Early observations from Earth-based telescopes revealed only a featureless orange disk, leading some astronomers to initially underestimate Titan's size because they were observing the top of its atmosphere rather than the solid surface beneath. Only when Voyager 1 conducted close flybys in 1980 did scientists realize that Titan's apparently large size actually resulted from its enormous atmospheric envelope. Thermal structure within Titan's atmosphere creates temperature gradients that drive atmospheric circulation and enable the condensation cycles that power Titan's weather systems. Surface temperatures average about -290 degrees Fahrenheit, 179 degrees Celsius. Cold enough that water ice becomes as hard as granite while allowing methane and ethane to exist as liquids. Temperature decreases with altitude through the troposphere, reaching minimum values around -320 degrees Fahrenheit, 195 degrees Celsius at the tropopause, before increasing again in the stratosphere due to solar heating of atmospheric hydrocarbons. The atmospheric circulation patterns on Titan operate according to fluid dynamics principles similar to those governing Earth's weather, but with rotation rates, temperature gradients, and chemical compositions that create entirely different circulation regimes. Titan's slow rotation. The Moon is tidally locked to Saturn with a 16-day rotational period, creates weak, Coriolis effects that allow different circulation patterns to develop than those found on rapidly rotating worlds like Earth or Jupiter. Seasonal atmospheric changes on Titan result from Saturn's 29.5-year orbital period around the Sun, creating atmospheric seasons that last over 7 Earth years each. These long-term seasonal cycles drive hemispheric atmospheric circulation patterns that transport methane vapor from summer to winter hemispheres, creating seasonal differences in cloud formation, precipitation patterns, and surface lake levels that play out over decades rather than months. The atmospheric optical depth created by Titan's organic haze makes the Moon's surface completely invisible to optical wavelengths, requiring infrared and radar observations to study surface features and geological processes. This atmospheric opacity results from photochemical processes that create tiny organic particles suspended throughout the atmosphere, giving Titan its characteristic orange color while preventing direct optical observations of the surface that lies hidden beneath this hydrocarbon smog. Atmospheric dynamics on Titan include wind systems, convection patterns, and storm formation that create weather phenomena unique in the solar system. Methane clouds form through condensation processes similar to water cloud formation on Earth, but operating at temperatures and pressures that create different cloud physics and precipitation mechanisms. These methane weather systems carve drainage channels, fill lake basins, and redistribute organic compounds across Titan's surface through meteorological processes. The energetics of Titan's atmospheric circulation involve heat transport mechanisms that distribute thermal energy from equatorial to polar regions, while driving the global circulation that maintains atmospheric chemical gradients. Radiative heating from the Sun provides energy input at high altitudes where atmospheric hydrocarbons absorb solar radiation, while infrared cooling to space creates the temperature gradients that drive convection and atmospheric motion. Atmospheric chemistry on Titan operates through photochemical reactions that create organic complexity impossible in most solar system environments. Solar ultraviolet radiation breaks apart methane and nitrogen molecules, creating reactive fragments that recombine into increasingly complex organic compounds. These atmospheric chemical factories produce molecules containing carbon-nitrogen bonds, aromatic hydrocarbons, and complex polymers that eventually settle to the surface as organic sediments. The atmospheric greenhouse effect on Titan differs fundamentally from greenhouse warming on planets like Venus or Earth because the atmospheric composition and temperature regime create different radiative transfer properties. Titan's atmosphere is essentially transparent to solar radiation, but absorbs thermal infrared radiation emitted by the surface, creating modest greenhouse warming that raises surface temperatures by approximately 20 degrees Fahrenheit above what they would be without atmospheric heating. Comparative analysis of Titan's atmosphere with other planetary atmospheres reveals both similarities and fundamental differences that highlight the unique conditions required for thick atmospheric retention on moons. While Titan's nitrogen-rich composition resembles Earth's early atmosphere, the methane component and organic chemistry create chemical processes that have no terrestrial parallels, demonstrating how different starting materials and environmental conditions can create entirely different atmospheric evolution pathways. Future atmospheric studies of Titan will focus on understanding the long-term evolution of atmospheric composition, the sources and sinks that maintain methane abundance over geological timescales, and the atmospheric chemistry that continues producing organic complexity. These investigations will enhance our understanding of atmospheric physics while searching for chemical signatures that might indicate biological processes operating within Titan's unique atmospheric surface system. The magnitude and complexity of Titan's atmosphere establishes this moon as a natural laboratory for studying atmospheric physics under conditions impossible to replicate elsewhere in the solar system, while demonstrating that moons can develop atmospheric systems rivaling those of planets when the right combination of size, composition, and environmental factors enables atmospheric capture and retention over billions of years. Chapter 2. Atmospheric Retention. The physics of atmospheric retention represents one of the most fundamental challenges facing any world that hopes to maintain a gaseous envelope over geological timescales. Yet, Titan has not only solved this cosmic puzzle, but done so with such spectacular success that it maintains the solar system's second densest atmosphere after Venus. Understanding how Titan accomplishes this atmospheric feat requires exploring the delicate balance between atmospheric escape mechanisms that strip away gaseous envelopes and the gravitational, magnetic, and chemical processes that enable atmospheric persistence over billions of years. Atmospheric escape occurs through several distinct physical mechanisms that operate simultaneously to remove atmospheric particles from planetary and lunar environments. Thermal escape, also called Huygens escape, happens when atmospheric molecules acquire enough thermal energy to exceed the escape velocity required to break free from gravitational attraction. Hydrodynamic escape involves bulk atmospheric flow away from the body when heating rates exceed the atmosphere's ability to radiate energy efficiently. Non-thermal escape mechanisms include sputtering by energetic particles, pickup ion loss, and impact erosion that can blast away atmospheric materials through high-energy interactions. The escape velocity from Titan's surface reaches 2.64 kilometers per second, substantially lower than Earth's 11.2 kilometers per second, but high enough to retain most atmospheric constituents under current temperature conditions. This escape velocity results from Titan's mass of 1.345 times Yd kilograms, about 1.8% of Earth's mass distributed across its 3,200-mile diameter. The relatively low escape velocity means that Titan exists near the threshold between worlds that can retain substantial atmospheres and those that lose atmospheric materials to space over cosmic timescales. Thermal escape rates depend exponentially on the ratio between atmospheric temperature and molecular mass, following Maxwell-Boltzmann distribution principles that govern molecular velocity distributions in gases. Hydrogen, being the lightest and most energetic atmospheric constituent, escapes most readily from Titan's atmosphere at rates of approximately 1.5 times 1,025 molecules per second. Heavier molecules like nitrogen and methane have much lower escape rates, allowing Titan to maintain these atmospheric components over billion-year timescales despite ongoing atmospheric loss. The temperature profile of Titan's upper atmosphere critically determines escape rates by controlling how many atmospheric molecules acquire velocities exceeding escape velocity. Titan's upper atmosphere reaches temperatures of about 150 to 200 Kelvin, 190 to minus 100 degrees Fahrenheit, much cooler than the 1,000 Kelvin temperatures found in the upper atmospheres of inner solar system planets. These lower temperatures dramatically reduce thermal escape rates, enabling atmospheric retention that would be impossible if Titan orbited closer to the Sun. Gravitational binding energy calculations reveal why Titan can retain nitrogen and methane, while smaller moons lose even heavier atmospheric constituents. The gravitational binding energy per molecule depends on both the escape velocity and the atmospheric temperature, creating a retention parameter that determines which atmospheric species can survive over long time periods. Titan's gravitational field, while weak compared to terrestrial planets, proves sufficient to bind nitrogen and methane molecules under the cold temperature conditions prevailing in the outer solar system. Solar wind interactions with Titan's atmosphere create non-thermal escape mechanisms that compete with gravitational retention to determine atmospheric evolution over geological timescales. Unlike planets with strong magnetic fields that deflect solar wind particles, Titan orbits within Saturn's magnetosphere and experiences bombardment by energetic particles that can sputter away atmospheric constituents through momentum transfer processes. However, Titan's location within Saturn's magnetic environment actually provides some protection from the most intense solar wind effects. The atmospheric chemistry on Titan creates both sources and sinks for atmospheric constituents that affect long-term atmospheric evolution. Photochemical reactions driven by solar ultraviolet radiation continuously break apart methane molecules, creating hydrogen gas that readily escapes to space while producing heavier hydrocarbon molecules that remain gravitationally bound. This atmospheric chemistry represents a complex balance between methane destruction and production processes that must be maintained for atmospheric stability. Atmospheric composition evolution over Titan's 4.5 billion year history reveals how atmospheric retention mechanisms have operated over cosmological timescales. Current atmospheric methane abundance indicates that either methane has been continuously replenished from internal sources or the atmosphere formed more recently than the Moon itself. Methane's photochemical lifetime in Titan's atmosphere spans only 10 to 100 million years, implying that atmospheric methane would disappear completely without ongoing replenishment mechanisms. The role of Titan's size in atmospheric retention becomes clear when comparing atmospheric properties with other large moons in the solar system. Ganymede and Callisto, despite being comparable or larger than Titan, possess only tenuous atmospheres because their formation in Jupiter's system provided different chemical inventories and thermal histories. Europa and Io experience strong tidal heating and magnetic field interactions that strip away atmospheric materials, preventing thick atmosphere development despite their substantial sizes. Atmospheric condensation and sublimation processes create seasonal atmospheric variations that affect retention by temporarily removing and returning atmospheric constituents to the gaseous phase. Methane and other hydrocarbons can condense into liquid or solid phases at Titan's surface, creating atmospheric reservoirs that moderate atmospheric composition over seasonal and longer timescales. These phase change processes provide buffer mechanisms that help maintain atmospheric stability against escape losses. The atmospheric lifetime calculations for different constituents reveal the timescales over which various atmospheric components can persist in Titan's environment. Nitrogen, comprising 95% of Titan's atmosphere, has atmospheric lifetimes exceeding the age of the solar system under current escape rate conditions. Methane lifetimes are much shorter due to both photochemical destruction and thermal escape, requiring ongoing replenishment to maintain observed atmospheric abundances. Atmospheric shielding effects help protect lower atmospheric layers from the energetic particle bombardment that drives non-thermal escape mechanisms. Titan's thick atmosphere creates sufficient optical depth to absorb most solar ultraviolet radiation and energetic particle flux before they can penetrate to lower altitudes, creating a self-protecting mechanism where atmospheric density enables atmospheric retention by shielding deeper layers from escape-driving energy sources. Impact erosion represents another atmospheric loss mechanism, where asteroid and comet impacts can blast away significant atmospheric masses through shock wave interactions and ejecta formation. Titan's location in the outer solar system reduces impact rates compared to inner solar system environments, while its thick atmosphere provides some protection against smaller impactors that burn up during atmospheric entry, rather than reaching the surface with enough energy to drive atmospheric escape. The magnetic field interactions between Titan and Saturn as magnetosphere create complex particle precipitation patterns that affect atmospheric chemistry and escape rates through mechanisms unique among solar system moons. Titan's ionosphere, created by particle bombardment and photochemical processes, interacts with Saturn's rotating magnetic field to create electromagnetic effects that both energize atmospheric chemistry and drive particle escape through pickup ion mechanisms. Atmospheric modeling of Titan's retention mechanisms requires sophisticated computer simulations that integrate gravitational dynamics, thermodynamic processes, atmospheric chemistry, and electromagnetic interactions to predict atmospheric evolution over billion-year timescales. These models reveal that Titan's atmospheric retention results from a delicate balance of competing processes, with small changes in any factor potentially leading to dramatic atmospheric loss or different evolutionary pathways. Future studies of atmospheric retention on Titan will focus on measuring current escape rates, identifying the sources that replenish methane and other atmospheric constituents, and understanding how atmospheric properties have evolved since the Moon's formation. These investigations will provide crucial insights into atmospheric physics while testing our understanding of the processes that determine whether worlds can maintain the thick atmospheres necessary for complex surface chemistry and potentially biological processes. Comparative planetology studies of atmospheric retention throughout the solar system use Titan as a test case for understanding the conditions required for atmospheric persistence on moons and small planets. Titan's successful atmospheric retention demonstrates that size alone doesn't determine atmospheric evolution. The combination of gravitational field strength, thermal environment, chemical composition, and protective mechanisms must all align to enable long-term atmospheric stability. The lessons learned from studying Titan's atmospheric retention apply to understanding atmospheric evolution on exoplanets and exomoons throughout the galaxy, where similar physical processes determine whether worlds can maintain the gaseous envelopes that enable weather systems, surface chemistry, and potentially the environmental conditions necessary for life to emerge and flourish over cosmic timescales. Chapter 3: Formation Origins. The birth of Titan's atmosphere traces back to the chaotic earliest epochs of our solar system, when the giant planets were migrating through the primordial disk of gas and dust, capturing raw materials and forming moon systems through processes so violent and complex that they created the only thick atmosphere moon among hundreds of worlds orbiting the gas and ice giants. Understanding Titan's atmospheric origins requires exploring the cosmic construction zone where Saturn and its moons formed, examining how chemical inventories, temperature gradients, and gravitational dynamics combine to deliver the materials that would eventually become Titan's remarkable gaseous envelope. The formation of Saturn's moon system occurred within the circumplanetary disk of material that surrounded the growing giant planet during the solar system's first few million years. This disk contained the raw materials, rock, ice, and gas that would accrete into the diverse collection of moons we observe today, but the specific conditions within Saturn's formation region provided chemical inventories and thermal environments that differed dramatically from the circumplanetary disks around other giant planets like Jupiter. Chemical gradients within Saturn's circumplanetary disk determined which materials were available for incorporation into growing moons at different distances from the planet. Close to Saturn, temperatures remained high enough to vaporize water ice and most volatile compounds, creating regions where only rocky materials could condense. At intermediate distances where Titan formed, temperatures dropped sufficiently for water ice to remain solid while still allowing nitrogen and methane to exist as gases that could be captured by growing moons with sufficient gravitational attraction. The timing of Titan's formation relative to Saturn's atmospheric evolution critically influenced the chemical inventory available for atmospheric capture. Early in Saturn's formation, the giant planet was surrounded by a massive envelope of hydrogen and helium captured directly from the solar nebula, along with heavier compounds that condensed from the cooling gas. Titan formed during this epoch when volatile compounds like nitrogen, methane, and other hydrocarbons remained abundant in Saturn's circumplanetary environment. Gravitational capture mechanisms allowed the growing Titan to acquire atmospheric materials through several distinct physical processes that operated during the Moon's accretion phase. Direct gravitational capture occurred when Titan's growing mass created a gravitational field strong enough to bind atmospheric gases that would otherwise escape to space. Impact degassing released volatile compounds from comets and asteroids that delivered water, ice, and organic materials to the growing Moon. Gravitational focusing enhanced the delivery of volatile-rich materials by increasing impact rates of objects containing atmospheric precursor compounds. The accretion process itself generated significant thermal energy through gravitational potential energy release and impact heating, creating temperatures that could drive atmospheric formation through outgassing of volatile compounds incorporated into Titan's interior during formation. This accretional heating distinguished Titan from smaller moons that formed with insufficient gravitational energy release to drive extensive atmospheric outgassing, helping explain why atmospheric formation succeeded on Titan but failed on most other moons throughout the solar system. Differentiation of Titan's interior during and after formation created the internal structure that continues influencing atmospheric evolution today through ongoing outgassing and possibly subsurface ocean interactions. The separation of rocky materials toward Titan's center and water ice toward the surface during differentiation established density gradients and thermal structures that affect how volatile compounds move between interior reservoirs and the atmosphere over billion-year timescales. The role of nitrogen in Titan's atmospheric formation presents particular challenges for understanding atmospheric origins, because nitrogen doesn't readily condense at the temperatures and pressures prevailing during moon formation in the outer solar system. Current theories suggest that Titan's nitrogen might have originated from ammonia decomposition, cometary delivery, or capture from Saturn's early extended atmosphere, but determining which mechanism dominated requires understanding the specific chemical and thermal conditions during Titan's formation epoch. Methane sources during Titan's formation could have included direct capture from Saturn's circumplanetary disk, cometary delivery, or internal production through chemical reactions between carbon-bearing compounds and water under high-pressure conditions within Titan's interior. The abundance and isotopic composition of methane in Titan's current atmosphere provide clues about formation mechanisms, but interpreting these signatures requires understanding how atmospheric composition has evolved since formation through various chemical and physical processes. Comparative analysis of moon formation throughout the outer solar system reveals why Titan developed a thick atmosphere, while other large moons like Ganymede, Callisto, and Europa remained essentially airless. The chemical composition of circumplanetary disks around different giant planets, varying thermal conditions during formation, and different timing relative to giant planet atmospheric evolution all contributed to creating different chemical inventories and formation conditions that determined atmospheric formation potential. The influence of Jupiter's migration on Saturn's formation environment affected the chemical composition and dynamics of Saturn's circumplanetary disk during the epoch when Titan was forming. Jupiter's gravitational influence on the early solar system disrupted the distribution of volatile-rich materials and may have enhanced or reduced the delivery of atmospheric precursor compounds to the Saturn system, creating formation conditions that differed from what would have occurred if Jupiter had remained in a more distant orbit. Isotopic signatures in Titan's current atmosphere preserve information about formation processes and the sources of atmospheric materials, providing observational constraints on atmospheric origin theories. The ratios of nitrogen isotopes, carbon isotopes, and noble gas abundances in Titan's atmosphere reflect the chemical composition of source materials and the physical processes that delivered these materials during atmospheric formation. Timing constraints on atmospheric formation come from understanding the lifetime of Saturn's circumplanetary disk and the duration over which volatile compounds remained available for capture by growing moons. The solar system's early evolution involved rapid changes in temperature, pressure, and chemical composition as the solar nebula evolved and dispersed, creating narrow time windows during which atmospheric formation could occur through different mechanisms. The accretion rate of Titan during formation influenced atmospheric formation by determining how quickly the Moon acquired sufficient mass to gravitationally bind atmospheric materials while affecting the thermal environment through impact heating rates. Rapid accretion would have created high-temperature conditions that could drive extensive outgassing, but might also have prevented retention of the most volatile atmospheric components, while slower accretion might have favored atmospheric retention, but reduced the total inventory of volatile materials available for atmospheric formation. Computer modeling of Titan's formation environment integrates our understanding of circumplanetary disk evolution, chemical thermodynamics, and gravitational dynamics to predict the conditions under which thick atmospheric formation could occur. These models reveal that atmospheric formation required precise combinations of chemical inventory, thermal environment, and gravitational conditions that apparently occurred only once among all the moons forming around giant planets in our solar system. The preservation of Titan's primordial atmospheric components versus ongoing replenishment from internal sources represents a fundamental question about atmospheric origins that affects our understanding of how atmospheric composition has evolved since formation. If Titan's atmosphere primarily represents primordial material captured during formation, current atmospheric composition reflects formation conditions. If significant atmospheric replenishment has occurred, current composition may differ substantially from the original atmospheric inventory. Future investigations of Titan's atmospheric origins will focus on detailed measurements of isotopic compositions, trace atmospheric constituents, and atmospheric chemistry that can distinguish between different formation mechanisms while constraining the timing and sources of atmospheric materials. These studies will enhance our understanding of moon formation while providing insights into the cosmic processes that determine whether worlds develop the thick atmospheres necessary for complex chemistry and potentially life. The formation story of Titan's atmosphere reveals that atmospheric development depends on precise combinations of cosmic circumstances, appropriate chemical inventories, optimal thermal conditions, sufficient gravitational binding, and formation timing within narrow windows when volatile materials remain available for capture. Understanding these formation requirements guides the search for similar atmospheric worlds around other stars while demonstrating that thick atmospheric development represents a remarkable cosmic achievement that succeeded only once among the hundreds of moons orbiting giant planets in our solar system. Chapter 4. Size matters among the fundamental factors determining whether a moon can develop and retain a thick atmosphere. Physical size emerges as perhaps the most critical parameter, establishing the gravitational foundation upon which all other atmospheric processes depend. Titan, a substantial mass of 1.345 YD kilograms, creates an escape velocity of 2.64 kilometers per second, just strong enough to gravitationally bind nitrogen and methane molecules under the cold temperature conditions prevailing in the outer solar system. While smaller moons throughout the solar system lack the gravitational strength necessary to prevent atmospheric escape over geological timescales. The relationship between moon mass and atmospheric retention follows fundamental physics principles encoded in the Maxwell-Boltzmann distribution of molecular velocities and the exponential dependence of atmospheric escape rates on the ratio between thermal energy and gravitational binding energy. For any given atmospheric temperature, larger moons possess deeper gravitational potential wells that more effectively retain atmospheric molecules, creating a sharp threshold above which atmospheric retention becomes possible and below which atmospheric loss dominates over atmospheric accumulation. Gravitational binding energy calculations reveal why Titan succeeds in atmospheric retention while most other moons fail despite receiving similar chemical inventories during formation. The gravitational binding energy per atmospheric molecule equals the molecular mass times the escape velocity squared, creating exponentially stronger atmospheric retention for more massive moons. Titan's gravitational field, while modest compared to terrestrial planets, proves sufficient to bind atmospheric constituents that would rapidly escape from smaller moons, even under identical thermal and chemical conditions. Comparative analysis of moon masses throughout the solar system demonstrates that Titan occupies a unique position in the mass distribution of natural satellites, large enough to enable atmospheric retention, but not so massive as to create the tidal heating or magnetic field interactions that might disrupt atmospheric stability. Ganymede, Jupiter's largest moon, exceeds Titan's mass by nearly 20% but orbits within Jupiter's intense magnetic field environment that strips away atmospheric particles through electromagnetic interactions that do not affect Titan within Saturn's more benign magnetosphere. The critical mass threshold for atmospheric retention depends on both the escape velocity determined by moon size and the thermal environment determined by distance from the Sun and internal heating sources. In the outer solar system where Titan resides, lower temperatures reduce molecular velocities and atmospheric escape rates, allowing smaller moons to potentially retain atmospheres that would be impossible in warmer inner solar system environments. Titan's mass places it just above this temperature-dependent retention threshold. Surface gravity effects resulting from Titan's size influence atmospheric structure and dynamics in ways that enhance atmospheric retention while enabling the complex circulation patterns that drive Titan's weather systems. With surface gravity approximately 14% of Earth's value, Titan's atmosphere can extend to much greater heights while maintaining significant density, creating atmospheric scale heights that enhance atmospheric mass while reducing atmospheric escape rates from the upper atmosphere, where most atmospheric loss occurs. The atmospheric mass that Titan can support scales with surface area and gravitational acceleration, creating atmospheric loading pressures that affect geological processes, surface chemistry, and the stability of liquid methane and ethane at the surface. Titan's thick atmosphere creates surface pressures 1.5 times greater than Earth's sea level pressure, enabling liquid hydrocarbon stability and complex atmospheric surface interactions that would be impossible on smaller moons with insufficient gravitational attraction to maintain substantial atmospheric masses. Tidal effects between Titan and Saturn result from gravitational interactions that depend on both Titan's mass and its orbital distance, creating internal heating through tidal flexing while potentially affecting atmospheric retention through tidal atmospheric distortion. Titan's substantial mass makes tidal heating less extreme than on smaller moons like Io or Europa, preventing the atmospheric stripping that intense tidal heating might cause while providing modest internal energy sources that could contribute to atmospheric replenishment mechanisms. The relationship between moon size and magnetic field generation affects atmospheric retention through electromagnetic interactions with the parent planet's magnetosphere. Titan's size proves insufficient to generate an intrinsic magnetic field through dynamo action in its interior, but this actually benefits atmospheric retention by avoiding the magnetic field interactions that can accelerate atmospheric escape through electromagnetic processes that affect magnetized moons in different ways. Atmospheric chemistry complexity scales with atmospheric mass and density in ways that favor thicker atmospheres maintained by more massive moons. Titan's substantial atmospheric inventory enables multi-step photochemical reactions that produce the complex organic molecules found nowhere else in the solar system, demonstrating how atmospheric mass provides the chemical buffering and reaction volume necessary for sophisticated atmospheric chemistry to develop and persist over geological timescales. The thermal inertia of Titan's massive atmosphere moderates temperature variations and creates atmospheric circulation patterns that redistribute thermal energy across the moon's surface. Smaller moons with thinner atmospheres experience more extreme temperature variations that can destabilize atmospheric retention through enhanced thermal escape during warm periods. While Titan's atmospheric thermal mass provides stability against temperature fluctuations that might otherwise drive atmospheric loss. Atmospheric layering and vertical structure depend on atmospheric mass and gravitational acceleration in ways that create the stratified atmospheric environments observed on Titan but absent on smaller moons. The pressure and density gradients within Titan's atmosphere enable distinct tropospheric and stratospheric layers with different chemical and thermal properties, creating the vertical atmospheric structure necessary for complex weather systems and photochemical processes. Impact protection provided by Titan's thick atmosphere results directly from the atmospheric mass that only sufficiently large moons can maintain, creating a protective buffer against smaller impactors that burn up during atmospheric entry rather than reaching the radiant surface with enough energy to cause atmospheric erosion. This atmospheric shielding creates a positive feedback mechanism where atmospheric mass enables atmospheric protection against impact-driven atmospheric loss. The accretion efficiency during formation scales with moon mass through gravitational focusing effects that enhance the capture of volatile rich materials needed for atmospheric formation. Larger moons like Titan could more effectively capture atmospheric precursor materials during formation through enhanced gravitational cross-sections and stronger gravitational binding of captured materials, explaining why atmospheric formation succeeded preferentially on the largest moons in each giant planet system. Orbital dynamics and stability depend on moon mass through gravitational interactions with other moons and the parent planet, affecting long-term atmospheric evolution through orbital changes that might alter thermal conditions or tidal effects over billion-year timescales. Titan's substantial mass contributes to orbital stability that maintains consistent thermal and chemical conditions necessary for long-term atmospheric persistence. The observational selection effects in studying moon atmospheres favor detection of thick atmospheres on large moons. But the physical absence of thick atmospheres on most large moons throughout the solar system demonstrates that size alone doesn't guarantee atmospheric development. Titan's atmospheric success required not just sufficient mass, but also appropriate chemical composition, thermal conditions, and formation timing that align to enable atmospheric capture and retention. Future studies of moon atmospheric retention will use Titan as a benchmark for understanding the mass requirements for atmospheric stability while investigating how other factors like composition, thermal environment, and magnetic field interactions modify the mass thresholds necessary for atmospheric retention. These studies will guide predictions about atmospheric possibilities for exomoons orbiting giant planets throughout the galaxy. The scaling relationships between moon mass and atmospheric properties revealed by studying Titan provide fundamental insights into planetary science that apply to understanding atmospheric evolution on planets, moons, and other worlds throughout the universe. Size emerges as a necessary but not sufficient condition for atmospheric development, establishing the gravitational foundation upon which other atmospheric formation and retention mechanisms can build. The remarkable fact that Titan represents the only thick atmosphere moon among hundreds of natural satellites throughout our solar system demonstrates how rare the combination of sufficient size with appropriate chemical and thermal conditions truly is, revealing that atmospheric development represents a cosmic achievement that requires precise alignment of multiple factors that apparently occurred only once in our solar system's 4.5 billion year history. Chapter 5. Chemical Composition. The chemical composition of Titan's atmosphere represents one of the most remarkable chemical laboratories in the solar system, where nitrogen and methane undergo continuous photochemical reactions that create complex organic molecules found nowhere else in our cosmic neighborhood. This atmospheric chemistry operates according to principles fundamentally different from the oxidizing environments found on terrestrial planets, creating a reducing chemical regime that enables organic synthesis pathways impossible in oxygen-rich atmospheres like Earth's. Nitrogen dominates Titan's atmospheric composition at 95%, providing an inert background gas that prevents the oxidation reactions that would destroy organic compounds in oxygen-rich environments. This nitrogen abundance creates chemical stability that allows complex hydrocarbons and nitrogen-bearing organic molecules to accumulate and persist over geological timescales, building molecular complexity through photochemical processes driven by solar ultraviolet radiation and energetic particle bombardment from Saturn's magnetosphere. Methane comprises approximately 5% of Titan's atmospheric composition, but this percentage dramatically understates methane's importance in driving atmospheric chemistry, weather systems, and surface geology. Methane's presence in Titan's atmosphere enables the complex hydrocarbon chemistry that produces dozens of organic compounds while providing the volatile component that drives atmospheric condensation cycles analogous to Earth's water cycle, but operating with entirely different chemical materials at much lower temperatures. The organic chemistry occurring in Titan's atmosphere produces an extraordinary inventory of carbon-bearing molecules through photochemical reaction networks that begin with methane photodissociation and nitrogen activation by solar radiation. These reactions create reactive molecular fragments, methyl radicals, nitrogen atoms, hydrogen atoms that recombine through hundreds of different pathways to produce increasingly complex organic molecules including acetylene, ethane, propane, benzene, and nitrogen-bearing compounds like hydrogen cyanide. Photochemical processes in Titan's upper atmosphere operate through mechanisms driven by solar ultraviolet radiation that breaks apart methane and nitrogen molecules, creating the reactive species necessary for organic synthesis. The energy provided by solar photons at ultraviolet wavelengths proves sufficient to break chemical bonds in atmospheric molecules, but the cold temperatures in Titan's atmosphere prevent most thermal decomposition, reactions that would destroy organic products as quickly as they form. The atmospheric organic haze that gives Titan its characteristic orange appearance consists of complex polymer particles formed through gas phase chemistry in the upper atmosphere. These haze particles represent the end products of atmospheric photochemical networks, containing polycyclic aromatic hydrocarbons, nitrogen heterocycles, and other complex molecules that eventually settle to Titan's surface as organic sediments that may accumulate to substantial depths over geological timescales. Isotopic composition of atmospheric constituents provides crucial information about the sources of atmospheric materials and the chemical processes that have operated throughout Titan's history. The nitrogen isotope ratios in Titan's atmosphere suggest either isotopic fractionation during atmospheric escape processes or inheritance from source materials with distinct isotopic signatures, while carbon isotope ratios reflect the balance between different carbon sources and atmospheric chemical processing. Trace atmospheric constituents include hydrogen 0.1%, argon, and dozens of organic compounds present in parts per million or parts per billion, concentrations that nonetheless play important roles in atmospheric chemistry and provide information about chemical reaction networks. These trace species include acetylene, ethane, propane, hydrogen cyanide, carbon dioxide, and water vapor, creating a complex chemical inventory that reflects the diversity of reactions occurring in Titan's atmospheric chemical laboratory. The vertical distribution of atmospheric chemicals creates chemical layering that reflects the altitude dependence of photochemical production rates and atmospheric mixing processes. Methane concentrations increase toward Titan's surface due to evaporation from surface lakes and the condensation of photochemical products at higher altitudes, while complex organic molecules show maximum concentrations at intermediate altitudes where photochemical production rates peak. Chemical equilibrium considerations reveal that Titan's atmospheric composition represents a steady-state balance between chemical production and loss processes rather than thermodynamic equilibrium. Methane photodissociation continuously removes methane from the atmosphere while producing hydrogen that escapes to space in carbon-bearing radicals that form complex organic molecules. This chemical disequilibrium requires ongoing methane replenishment to maintain observed atmospheric methane abundances. Atmospheric chemistry modeling requires sophisticated computer simulations that track hundreds of chemical reactions operating simultaneously under Titan's specific temperature, pressure, and radiation conditions. These models reveal how solar energy input drives chemical complexity while predicting the atmospheric chemical composition that should result from different assumptions about methane sources, atmospheric mixing rates, and surface chemical interactions. The organic molecule inventory in Titan's atmosphere includes molecules of astrobiological significance compounds that serve as building blocks for biological systems on Earth and might potentially support alternative biochemistry under Titan's exotic conditions. Hydrogen cyanide, acetylene, and other molecules detected in Titan's atmosphere participate in prebiotic chemistry pathways that could potentially lead to more complex biological molecules given appropriate catalytic surfaces and energy sources. Surface-atmosphere chemical interactions involve exchange processes between atmospheric constituents and surface materials that affect both atmospheric composition and surface chemistry. Methane and other hydrocarbons can dissolve in surface lakes, while organic compounds produced in the atmosphere settle to the surface, creating chemical cycling that connects atmospheric and surface chemistry through complex feedback mechanisms that operate over various timescales. Seasonal chemical variations result from atmospheric circulation changes that redistribute chemical species between different altitude levels and hemispheric regions during Titan's 29.5-year seasonal cycle. These chemical seasons create temporal variations in atmospheric composition that affect photochemical reaction rates, organic haze production, and the surface chemistry occurring in different regions as chemical inventories change over time. Laboratory experiments attempting to replicate Titan's atmospheric chemistry use specialized reaction chambers that simulate Titan's temperature, pressure, and radiation conditions while starting with methane-nitrogen gas mixtures similar to Titan's atmosphere. These experiments reveal how complex organic chemistry develops under Titan-like conditions while producing organic materials that can be analyzed to understand the chemical processes operating in Titan's real atmosphere. The chemical stability of organic compounds in Titan's atmosphere depends on the reducing chemical environment created by the absence of oxygen and the presence of abundant hydrogen-bearing species. This reducing chemistry prevents the oxidation reactions that would rapidly destroy organic molecules in oxygen-rich environments, allowing organic complexity to build over time through cumulative photochemical synthesis rather than being continuously destroyed by oxidative breakdown. Analytical challenges in studying Titan's atmospheric chemistry include the difficulty of detecting trace organic compounds from spacecraft observations and the complexity of interpreting mass spectrometer data in the presence of complex organic mixtures. Advanced instrumentation capable of identifying specific organic molecules in Titan's atmosphere continues to be developed for future missions that will provide more detailed chemical analysis of atmospheric composition. The implications of Titan's atmospheric chemistry extend beyond planetary science to questions about prebiotic chemistry, alternative biochemistry, and the chemical processes that might support life in environments very different from Earth. Titan's atmospheric chemistry laboratory demonstrates that complex organic synthesis can occur through purely atmospheric processes, suggesting that similar chemistry might operate in the atmospheres of exoplanets throughout the galaxy. Future chemical studies of Titan's atmosphere will focus on identifying specific organic molecules, understanding chemical reaction networks in greater detail, and determining how atmospheric chemistry connects with surface chemistry through chemical cycling processes. These investigations will advance our understanding of atmospheric chemistry while exploring the chemical complexity that emerges when reducing atmospheric chemistry operates over billion-year timescales. The extraordinary chemical richness of Titan's atmosphere reveals that atmospheric chemistry can achieve levels of molecular complexity previously thought to require biological processes, demonstrating that complex organic chemistry represents a natural consequence of atmospheric photochemistry operating under appropriate chemical and physical conditions over geological timescales.